So our second seminar of the day is given by Atikur, and he's going to be presenting a risk utility balancing approach to generate synthetic microdata.
Good evening. I am not an expert of synthetic data. Experts are sitting in front of me. I'm here to share my problems when I started to generate some synthetic data to mask a data matrix that came from smart grid, smart city data. But I encountered the problem when I was trying to mask the data matrix. The problem was the computation of risk and the utility. So it was really very hard to convince from where I start and which set of data I should release after synthetic data generation. So to generate the synthetic data, the first thing is, what is synthetic data? The definition is, I'm not going to provide the definition. The thing is that anything on the original data, if we change the original data or alter the original data, that can be synthetic data. That sort of concept has been used in many literatures in early 60s, even in some engineering literatures, even in some biological sciences. But in terms of statistical disclosure control, so we think that there should be some model. The data that we are going to generate to mask the original data matrix, this should be based on some statistical models. And the data that we are going to generate based on some statistical model would at least hold two properties. The first one is the generated data should reduce the chance of re-identification of data subjects or some sensitive attributes of data subjects. And the next one is, we can feed different models, we can generate data from different models. But after generating the data, whether the data is holding the property of the original data set. So these concepts then raise the matter of data utility. So if the generated data set holds the properties, inferential property of the original data set correctly, then we said there's good utility of the data. But if this doesn't, then probably there is no use of the synthetic data. So here we come up to problem. One is to reduce the risk, another is to ensure the utility of data. But these two things are not possible to optimize at the same time, because now the risk is minimum, then utility is also minimum. But if you want to maximize the utility, this comes with the maximum chance of disclosure of subject's identity. So what we need to do, we need some balancing. Compensate either the utility or the risk or the both. So that was the problem. So here I'm considering only the continuous data, not the categorical or discrete ordinal data. There are some good measures to calculate the probability of re-identification for categorical or binary response data. But for continuous data, that is not that strict, because we can interpret that in terms of probability. Because there is no exactness, this can be, generated data can be very close to the original data, but there is no exactness like 1 to 1, 0 to 0. So we need to consider some, measure. We are not going to compare the performance of different measures. So there are plenty of measures here, but I'm going to point only few. One is the distance-based disclosure risk measure. Another is the utility measure that is also comes from some distance-based computation. So for my analysis, I'm considering in interval disclosure option to find the mass. I mean the closed generation of data within the interval. So I'm considering this measure for my data analysis at the later stages. Now we can start with the many model, but before going to set my problem, I'm going to start talking from the base. The most commonly adopted synthetic data generation technique is to add the noise to the original data matrix. That is masking the matrix. So what we do generally here, we got a data matrix, then we generate a noise matrix, then add the noise matrix with the data matrix. To get the matrix is X star. This is the original matrix, this is the noise matrix. Now, how to generate this noise matrix? This can be based on the strength of the original data matrix. As done by other authors, this can be based on the percentage of strength, like P times the covariance matrix or something like that. But in statistics, we can say this is the signal to noise ratio. The signal to noise ratio is the trace of the original matrix and trace of the noise matrix. So here, so what we can do then, we can select this noise covariance matrix based on some signal to noise ratio. We don't know which signal to noise ratio is perfect for generation of specific synthetic matrix. So, but we have to assess one by one signal to noise ratio 1, 2, or 100 or 1,000. We don't know. Then another approach is the resampling technique. So what we can do, we can resample the row of the data matrix and generate different versions of data matrix X1 to XR. And as noted by some other author, that take the average of all the generated matrix. But if R goes to infinity, if R becomes sufficiently large, then in fact we are replacing each of the element of the matrix by the average of variables. So this converges to the mean. Now, this is Energy Information Authority data, has been used by CSIRO project. There are 3 reference data sets, so this is one of the reference data sets. Yeah. So here is the signal to noise ratio. This is equal to 1. This means 50% signal, 50% noise. So signal and noise are independent. So we cannot expect 50% of utility because we don't know the true distribution of the matrix X, but we know the true distribution of the noise. So whatever inference we are drawing from the synthetic data is influenced by the noise matrix, not by the original data matrix. So here we see this is the loss one, utility loss measure, distance-based loss measure, and this is the distance-based risk measure. The risk is very low. This should be, because signal to noise ratio is equal to 1, 50% signal, 50% noise. This should be very small. But the utility is horrible in the sense because all inferences are going to be dominated by the noise process. Then if we increase the signal to noise ratio to 10, then this is going up. This increased a little bit. But in theory, signal to noise ratio, whatever, doesn't matter. The relation should be something like this. The pattern should be like this, because this is loss measure and this is risk measure. The utility and risk measure should be like this, but this should be negative, not showing even any pattern like this. Anyway, so if we increase the signal to noise ratio further, this is going to be a nice good shape. But signal to noise ratio is 100. If we increase the signal to noise ratio further, then to 1000, now the risk is going up, much higher compared to this and this and this. But the loss function is here. Loss function is not jumping so high compared to the risk here. So what we need to ensure that we are using a right risk metric and right utility metric. This is a challenge till now. We don't know exactly what will be the exact method, but people are working still in this domain. Now, we can just remember this code here. There are several versions from Ronald Coase, but we don't know exactly which one is the correct. I coined this from here, bias in research, by Anna, published in 2013. So if you torture the data long enough, it will confess to anything. Yes, it is, because we tortured a lot, so the utility is really horrible. Of course, the risk is 0. So we should not infuse too much noise with the data matrix to mask a matrix. We must control the amount of noise to mask a data matrix. So to do that, we try different other options. So to try this, let's think about the decomposition of the data matrix. To set the scene, let's assume that x onto xn be an observed realization of the process. This is the m-dimensional process xi with finite mean mu and finite covariance matrix gamma. So the singular value decomposition of the data matrix X, here xi is this column vector. Now the centered version of this data matrix is this, and we can decompose this centered data matrix UDV transpose with usual notation of singular value decomposition. So here it is the diagonal matrix as usual in the notation of singular value decomposition. Now, from that one, we can generate the data. To generate the data, what we can do, we can hold other fixed, means the matrix D and matrix B. We can hold that fixed, and we can resample the rows of the matrix U. So this sort of resampling technique has been used in many other literatures, including functional data analysis, singular spectrum analysis, and some other models, and some other longitudinal models too. But most of the theories developed behind this is due to the Slutsky and Pillai 2013 and Hanlin-Chang 2015.
So why do you need to center it first before you do this approach?
I mean, this centering?
Yeah, I mean, is it just computationally it's more stable to do?
No, this is because of to mess with the theories coming later.
Okay.
Because if we want to compare the eigenvalues and the singular values, then we need this, because singular value decomposition can be based on only these. But if we want to think about eigen decomposition, the eigen decomposition comes from the decomposition of the covariance matrix. And the theories coming later are based on the eigenvalues of covariance matrix. So to integrate the distribution of D square is essentially D is the singular values, but D square is the eigenvalue. So later we have to, I want to connect this D square with the eigenvalue L, and then later I want to integrate this idea with the Slutsky's theorem to derive the distribution of eigenvalues to assess the utility at some point. That is why I'm using centered fashion from the beginning to keep consistency with the theorem. But if you want, you can do just with the original matrix. This is not a problem. So here we can resample from the EU. So most of the theories are coming from these two applications here. Then the synthetic data, I mean the generated data matrix is X star coming like this. Now let's see what happened. The risk and utility measure we have used. This is the distance-based measure used earlier. This is the utility loss function. And we use the EIA dataset. So here we see the spike. The shape is exactly what we want, but disconnected here. This is not smooth enough. So if you want to make it smooth, then the theory says, I'm not going to tell all theories here, but theory says we have to add some small amount of noise with U. Even just not like U star plus some noise. Then this will be smooth. So we are not going to follow this option either, because if we want to add some noise, even then we don't know the signal to noise ratio to generate the noise. This is another challenging task. Decide about the signal to noise ratio. So what should be the exact signal to noise ratio to generate noise matrix to add with this U star? We don't know that. Then we tried resampling from the Stiefel manifold. There are plenty of nice theories to resample data from Stiefel manifolds, but mainly used in functional data analysis and longitudinal data analysis or in singular spectrum analysis, and this sort of theories. So what we do here, then the columns of U are normalized eigenvectors of X transpose by N. That is why I used centered version at the beginning. So now this quantity is sample covariance matrix. And by definition, U transpose U equal to identity matrix. Then if that is, then this satisfies the condition that U is a point on the Stiefel manifold, m-dimensional and n-element Stiefel manifold. Then this is the space of m orthonormal vectors in n-dimensional space too. So what happens? We can generate m-dimensional vectors, m-dimensional matrix from this space, subject to the condition that there exists some distribution on that space. So what we can do here, we can generate U star for this U by taking IID random draws from a distribution supported on the Stiefel manifold. This manifold. Then compute the resampled data matrix X star by using this relationship. Now we see the EIA dataset. So we have generated 1,000 data matrix and computed risk and utility for each of them. So here the utility measure is very high. but the risk measure is not that high. In terms of disclosure risk measure, of course, this is not a probability, these are some measure. This is not too high, but it still, if you think about the information loss measure, this is too high. So it seems that by generating data from the Stiefel manifold, we're going to reduce the risk, but we cannot ensure enough utility. Now, we try some other thing like generating data from Slutsky's theorem. So here, this lemma is due to Khan and Puskit in 2010. They used this to generate some data for time series that apply to in the context of functional data analysis and singular spectrum analysis. So the probability generating mechanism xi, probability generating mechanism of m-dimensional vector xi that satisfied the mean converges to mu, sample mean converges to mu, and sample variance, the covariance converges to a positive definite matrix in limit. This is the Gramian gamma, and also holds this condition norm is the order of log n by n, square root log n by n. Then as n goes to infinity, this goes to 0, this goes to 0, and this also goes to 0. So in that case, we can show that the eigenvalues from this gamma is converges to the eigenvalues estimated from the sample covariance matrix.
And what is gamma? The true covariance matrix?
Yes, the true covariance matrix. So here, this is the original. I mean, this is the true eigenvalues, and this is Lj by n. Lj, then Lj is the eigenvalue obtained from x transpose, and we have divided by n, so that this is the eigenvalue obtained from this sample covariance matrix. Now, by Slutsky's theorem, we already showed that we already showed these convergence properties. Then we can, since these convergence hold, we can show that this holds, this distribution holds. Means this is the sample eigenvalue obtained from the sample covariance matrix, and this is the theoretical value obtained from the gamma, the Gramian gamma. And this is also here, this follows normal distribution with mean 0 and standard deviation 1. Since we know that we can compute the confidence intervals, but the one problem here is here is gamma, the gamma is here too. This seems like computing the confidence interval for Poisson mean. There are 19 different versions of confidence intervals to compute the confidence interval of Poisson mean. But the first one is developed in 1931, and last one I saw in 2009. So there are 19 different versions. So we can follow the word procedure to replace this by the estimated value, or we can generate from the data. I mean, we can get the generating mechanism of this, because this is the root. So if we find the root that generates this root, then we can generate the pool of that root, and we can compute the empirical distribution, as well as we can compute the mean and the variance of that. So by solving this equation, we can show that this is the root. The root can be estimated like this, but this z is in fact this one,
this happen in the synthetic ability? Hold on, it's coming back, is it? Okay, let's see. You might need to turn the projector on and off, but it's okay for now.
But we have to make sure that the root we are going to generate from the estimated value follows some boundary condition. At least one boundary condition is this should be greater than 0, because all eigenvalues for positive definite matrix is greater than 0. So we have to make sure that this becomes a positive always. So this is from, truncated partial of the distribution, 0, and the upper bound is this. So we got this, we have generated this Z from truncated normal distribution to make sure that the boundary condition of generated eigenvalues holds. Then another problem is we can generate eigenvalues to replace the matrix D by the eigenvalues, by some function of eigenvalues. But the matter is the total variation. So if the root differs from the original one, like, so what happens if we know this, then we can estimate this. But if we get this, then we can get the root. The problem is if we replace this in the diagonal matrix of eigenvalues, then the total variation may not equal to the variation of the original matrix. Means trace of x transpose by n may not equal to trace of x star transpose by n. So to control the total variation within the data matrix, we have to rescale the eigenvalues by using this rescaling. So if we do that, then the total variation of the original data matrix will be equal to the total variation of the synthetic data matrix. So that is why we use this rescaling. So once we calculate this rescaled version of eigenvalues, then we place this here. We can place this by this relationship here, and this here. Then we can calculate this, because there is a good relationship between singular values and eigenvalues. So in this way, we can generate the data matrix based on this Slutsky's theorem and the eigenvalue and singular value decomposition. Now, we can use many other resampling techniques to generate the data. But here the good thing is that we know the true parameter based on the relationship here, based on the root. We can calculate the root based on the estimated value. Since we know the root, we now know the population parameter that generates the data. So we got the estimated value of the parameter, we know the population parameter that generates the data. So we can compare the estimated parameter with the population parameter to compute the utility. So the simplest way that we did is we use the interval overlap measure that computes the probability of overlap of two confidence intervals. And we can also compute some other measure, Weapply measure too, because we know the distribution here. So now what we did here, we can generate the data based on either Stiefel manifold, resampling from Stiefel manifold, or resampling from the eigenvectors, or resampling from based on Slutsky's theorem. Whatever, we can do that. But the main challenge is to keep a good balance between data utility and risk measure. That is really very hard to maintain based on existing measures. So we think about the slider here. So this is not exact that we don't want, but this is an example of a slider. So what we can do, we can move the slider, to compensate between utility and risk, disclosure risk. We have to decide based on this how much utility at least I want and how much risk I can accept. So that is the main thing here. But we are going to talk something more about data analysis and how to implement this and what are the challenges to do that. So I have used 3 data sets, that are known as reference data set by CSIRO project. So these 3 data sets are the census data set that contains 13 variables with 1080 records. And the second one is US Energy Information Authority data. This contains 15 variables, but I have considered only 4. And the other is the Tarragona data. 13 quantitative variables, I have considered only 3 here. Because to keep the variation among dimensions, the 13, 4, and 3. Now let's see what happens here. So this is the distance-based risk measure and utility measure when we use the census data. So we generate 10,000 versions of X star based on Slutsky's theorem. So the disclosure risk measure, this is coming from here to here, and the utility measure, the IL1 actually, that I used earlier, but this is utility measure, just change the line. So here, in terms of loss, this is not huge, but the risk is not huge too. But it's really very hard to decide exactly how much I will consider, how much utility loss I will consider, and how much disclosure risk I will accept. Now, based on this interval overlap measure, so this is the disclosure risk based on distance measure, and this is the data utility measure based on the interval overlap measure. So here, 0.8. So what happens? Any sample, any X star falling right side of this line means that if we use this particular X star as generated synthetic data, then we will have at least 80% of data utility, because this is probability, probability. We can interpret something like this. Of course, original interval overlap measure ranges between 0 to 9.95. But if you divide by 0.95, just scale this, then this from 0 to 1. So at least, let's say at least 80% utility. Now, still what happens? This line, I'm going to interpret this later. So let's think about the original value of the risk measure. The lowest point here can be like this, above 0.4. Of course, this is not probability, so we don't need to worry much about that. But still, this is a measure. We must have to reduce as much as possible. So this line is the 20th quartile. So any value falling under this line refers that by using any of these X star, we are having the risk that is less than 80% of other X star. generated from this process. So one option is that if we think that I will have 80%, at least 80% utility, and I will compensate something like that. I will generate a huge amount of data or whatever. I will generate some data, and I want to select the synthetic data set such that this produces risk less than, at least less than 80% of other. So this is from the lower 28, lower 20th contract. So we can generate any set of data from this, if this is the criteria for acceptance of risk and utility. In that case, probably we'll select the lowest, with the lowest value of the disclosure risk measure. Now, if you move at another data set, then this is the Tarragona data. So here again we see the utility loss measure and disclosure risk measure, but disclosure risk measure is too high here, ranging even around 0.9, 5.1. So it's really very decide exactly how much risk I will accept here. This is really very challenging.
Can you remind us, the distance-based risk was the difference between 2 points? Can you remind us what the utility and the risk measure is?
This is the utility measure is based on the utility measure I have mentioned here at the beginning. This one.
That's the
Information loss.
That's the
That's the information loss measure. And if we use the same disclosure risk measure, distance-based measure, but with the utility measure based on the interval overlap, then we get this kind of picture here. So if we stick to 0.8, so this line 0.8, so any x star falling right to this line will have at least 80% utility. But still risk is very high. So one option is to think about, again, the lower 10% point or the 20% point, and this is the 20% point. So this part contains 80% of the generated X star. So any sample, any X star falling with this corner has at least 80% of data utility and risk less than 80%, highest 80% of risk. Now, this was the previous example was generating data based on the Slutsky's theorem and eigen decomposition. Now we generate data from the Stiefel manifold. So if we generate data from a Stiefel manifold, the utility measure looks like this, and risk measure. This is not too bad. But based on this, information loss measure, so this loss seems huge. Now, if we consider the interval overlap based utility measure, then this looks like this. So the utility is too low. But here we got only one. I don't know why we got this one. This is the risk is not too high compared to others, but the utility is very high compared to others.
So just because I'm sure I call that, but interval overlap measure, that's sort of overlap of confidence intervals, right?
Yes.
But based on what? For what statistics are you creating the confidence intervals for? What are you?
The distribution of eigenvalues.
Oh, okay, so this is the eigenvalue. So you've got a confidence interval for the eigenvalues.
Yes.
Okay.
Yes.
All right.
Because the total variation of X star and total variation of X are equal.
Okay.
And by convergence theorem, by Slutsky's theorem, eigenvalues from this is converging to the other. So we have computed interval overlap measure based on the estimated eigenvalue and the distribution of estimated eigenvalue.
I
So-
thought you were looking at things like in Tarragona, you had variables here.
Yeah,
Income,
that's what I was, yeah.
Turnover, receipts.
Yes, there are many other variables. I have selected only few. Probably the only one reason I can say, I had to finish running simulation before the presentation. Truly speaking. And another reason is
So, you know, the analyst doesn't care about the confidence interval and eigenvalue, they want to see what happens to income.
Yeah, so because basically what would be good to see is sort of some actual sort of statistical analysis of the data, because that's what, right, people will want to do a regression
So that's a good
and,
thing
yeah.
to move on to.
yeah, I shall look at this later probably sometimes.
Excellent.
Yeah, that's a very good idea. I have to do that if I want to use this data later, probably then I have to. What is the point of
Yeah.
using the generated data?
Yeah.
That's the good question. So we have to fit some model,
That's right.
but just at this moment, I'm going to and the classical approach is to. What about data we generate doesn't matter. The matter is we fit a model with that data, or we make some inferences based on that data, and we take the inference from the original data set as well as from the generated data set.
And then
Then either-
calculate that.
Yeah, then we either compare the discrepancy between two inferences, like if this is regression coefficient, then we can see the absolute distance or what is or something like this, or even confidence interval overlap of the estimated data. So something like this. So we have not done this yet, but we got on population parameter, that is gamma, and we estimated on population parameter, that is gamma hat. So we compared these two parameters to compute the utility. Probably in some later stages we will do some other analysis, and based on that analysis we will see how this procedure is performing in practice. And this is the EI dataset. Again, this is information loss measure. This is distance-based risk measure. So they're too high. And this is low. This is natural. This should be, because risk is very high, then information loss will be low. Now, if we replace this by our procedure, like the utility measure based on the estimated parameter and the population parameter, then we see again this is very high. Of course, we can get that there are some generated data matrix that provide sufficient utility, but if we think about this risk measure, then it's very, very high, nearly 1, very close to 1, the highest level. So now if we generate data from stable manifold again, then what happens for this data set? Then again, information loss is huge. Of course, the risk is very low. Now, if we replace this measure by the internal overlap measure based on the gamma and gamma hat, then here we see utility is not very high, even very high, not very high, though risk measure is not that very high. So here we can see for census data, in terms of risk and utility, probably when you are generating data from the eigenvalue decomposition and the Slutsky theorem, probably this is not too bad. But if we generate data from stable manifold, this becomes very worse. Like here, the one sure, probably not there. And here, if we generate data from for this one, Terragona data set from stable manifold, this is not bad. But if we generate data from Slutsky's theorem and eigenvalue decomposition, then risk measure is very, very high. So, data generation process from stable manifold is providing quite good result for one data set, but not performing well for other data set. And generating data from Slutsky's theorem is performing for one data set, but getting worse for other. And in the last example, here, for this data set, neither of the two are working well. Neither data generation process based on the Slutsky's theorem and eigenvalue decomposition, as well as from stable manifold working. So we got 3 different data sets and 3 different methods, but for this data set, none of them are working. Maybe we can go back to the original one. At the beginning, yeah, maybe one option is to infuse noise as much as possible. Then we can see from here, with equal strength of signal and noise, this is not very meaningful. But if we infuse some more noise, less stronger noise, then even not following the relationship between utility loss and risk. If you see here, this is providing some good pattern, but we don't know exactly how much noise we have to infuse. Probably we have to find some other good model to generate that data. Or if we add some noise, then we have to look at different options for signal to noise ratio, and we have to look which one I want to accept. If we replace this by the utility measure, because the utility measure based on interval overlap is coming from the distribution of eigenvalues, estimated eigenvalues. Since this is a data matrix, we can compute eigenvalues from the original data set. We can compute eigenvalues from X star as well. Then we can even if we use the signal to noise ratio process, we can compute sample eigenvalues. We can from X and sample eigenvalues from X star. Then we can compute interval overlap measure. Now, if we replace this, if we replace this by interval overlap measure, then there are some good shapes. Unfortunately, I don't have in the slide, but there are so many graphs. Exactly how much noise I shall infuse, I don't know. But this looks, that graphs look much better than this. We can easily trace out 80% point for utility. For risks, this in fact depend on the amount of signal to noise ratio. If we use signal to noise ratio 100, this shows within bound, means 80%, lower 25% point shows something like here, around 0.23. So that's good, but the problem is we don't know exactly how to select the signal to noise ratio. We have to select one by one. Then this is some sort of trial and error. So at the end, one conclusion that I can say only is there is no perfect model to generate the data. One model may be good for one data set, but may perform even worse for other data sets. So this depends on the structure of the data, because all data generating mechanism depends on some known process, but in practice, we don't know the true process of observed data. So we can only rely on a single model or single data generating process. In fact, what happens, all models are wrong, some models are useful, so something like this. My conclusion is from George Box said eventually all models are wrong, but some are useful. Yes, it is. We try different options. One generating process is working well with one data set, but performing worst for other data sets. So we have to, but the thing is that we have to consider the data generating mechanism, and we can try different options, and based on the options, and okay, we tried this 5. Among these 5, we got this is doing better. That we are always in relative world. So all measures are relative measures, like risk measures and utility measures. So we have to select the data generating process relatively, means try 5, this is providing good results, something like this. So at the end, I can say that probably our process is also wrong, but give it a try. This can be useful at some point. Thank you very much.
Okay, I'm not sure how strict we need to be at time, but we probably have a few minutes for questions anyway. So, does anyone want to ask anything? I think people are still on, maybe watching, so if they want to email me.
Just a very specific one. You said there were 2 key references in the middle. What were they?
IS and S.
For Slutsky's theorem.
Oh, that was just 2 Slutsky's theorem, was it?
Yes, Postkit and Sender Pillai. And another is Hanlin Shang.
Okay. But they include the limit theorems.
Postkit, Don Postkit, my PhD supervisor.
Right, okay.
And Hanlin Shang, when I started my PhD, he just finished his PhD. He's now at the Australian National University. So we did some work with Slutsky's theorem and singular value decomposition to identify signal from functional data from singular spectrum analytic forms and in many other ways. In fact, we started looking at synthetic data when I started working at CSIRO for the project that is about energy consumption from smart meter data. Then we started looking some options to generate synthetic data, but there are some time-stamped problems, so it's really very challenging to generate data, but satisfying the condition of risk and utility. Because as we know, all timesheets data has very low power, means even if you think about R square, it's very low, and mean square error is generally very high. So there are always some shortfall about the utility, so it's really very hard to find the data generating process based on some existing model. Then we started working on that. And so in the next phase, we are extending our work to timesheets analysis, generating synthetic timesheets.
Gillian has a question. So you made an interesting point at the end of your seminar that you need to find the signal to noise ratio by considering the structure of the data. Is this not what those of us who are creating synthetic data are always trying to do by fitting distributions to data sets? It's a good way to think of it.
Yes, that is, generally we feed data to, generally we feed some statistical model, and we generally generate data from that model. But what happens in some cases, maybe you don't know what is the good model. So rather going to fit the model like O equal to x beta plus epsilon, something like that, we are taking the, I mean, if you want to fit any model, but if your dependent variable is multivariate in nature, you don't have too many options to fit a model with the continuous data.
So I was going to ask you about as well, this is only for continuous data that you're defining, so you can't handle categorical data, right, at this point?
Yes, there is, you can do that, but the main challenge here is to prove the Slutsky's theorem, and match the Slutsky's theorem with the singular value decomposition of categorical data.
And
So the main problem is you can calculate covariance matrix, or think about the correlation matrix. You can calculate correlation matrix easily based on continuous data, but for categorical data you cannot.
And so does your data have to be multivariate normal, or can any continuous?
No, any type of continuous data that holds the assumption of single value decomposition.
Okay.
Even if that becomes non-linear process, still we can do that, because it is proved that singular value decomposition can be applied even if there exists a non-linearity within the data. Of course, there are several versions of singular value decomposition or eigenvalue decomposition, but think about principal component analysis. There are several versions based on the linearity, non-linearity, but under some regularity conditions, we can prove that even that if the data is non-linear, still you can apply single.
So no, you can do SVD, but would it work very well? I mean, because the idea is you want to know about the structure of your data so that you can generate a good synthetic version of it. And if your data is very non-normal, would you not be doing a bad job at sort of keeping the structure of the data, the type of data, statistical properties of the data?
I mean, yes, if you think about some theorem like Bartlett's theorem or something like this, then you need to impose the normality condition. Like if you want to select the number of components you want to use, like here we've got m-dimensional process, but you want to know the signal of the process, means you want to know the value of k less than m, and then based on first k principal component you want to generate the data. Then you need only, because selection of k depends on some assumption, and that assumptions are related to normality of the data. But we are using all eigenvalues, all m eigenvalues. We are not selecting or generating data from the lower dimensional space. So we have original data matrix that is in m-dimensional space. We are generating data from m-dimensional space too. We are not generating data from lower dimensional space, like k-dimensional space, k less than m. We are not doing that. If we do that, then we need assumption like normality. Otherwise, we can generate data even if that is not normal.
Are there any other questions? Let's thank our two speakers again then. Thank you very much. Dan, thank you for listening as well.
Just a quick word. I'm away tomorrow. So I just feel like it's
I went to the one yesterday. I think I've got a revision deadline to make.
So
So I need to send it to my collaborator by the end of tomorrow. She said this she's only got the weekend. So I've got to be.
we're all sure.
Well, I don't know, because I don't know where it is.
Yeah, Slutsky must have gone, but I don't know whether Christine was going, because she gave it to me yesterday. I think it's going to be so. I didn't want to. Oh, no, so that's right. No. Yeah, I think it's